So here is problem 9, and it's qualitative. The question is, which of the following reactions would you predict to have the largest orientation factor? So it gives us a list of 4 reactions, and we need to use our understanding of the orientation factor to understand which of these is the proper choice. Now remember, this is just purely how complex the molecule is. The more complex the molecule, and that means the more structural features it has, the tighter the approach must be of one atom or molecule to the other. And these are all molecules with the exception of the first, where it's atom H plus atom F. We think of these as spherical objects. It doesn't matter what their orientation is. It is a sphere approaching a sphere. The angle isn't even defined. It's symmetric with respect to everything. Br2, that's a linear molecule, Br sphere in line with another Br sphere, and that has to orient itself with this planar molecule, but it has 2 H's coming out of this end, 2 H's coming out of this end, and that Br has to add across that double bond. I mean, it requires a specific orientation. All of these do, with the exception of the atoms. So our atoms are going to be our best choice to have the largest orientation factor. It's going to be 1. It doesn't matter what the angle or orientation is of approach. So here is problem 10, still in chapter 15, and this is an activation energy problem where the activation energy doesn't change with temperature. That's a fixed number, nor does A change. So what we are given in this case is a rate constant at a temperature and the activation energy. So we can calculate the one thing we don't know, which is the A factor, and then do it at the second condition. So let me show you what I mean here. So here is the Arrhenius equation, and this is what I'm saying. I have rate constant, I have my activation energy. Now this has to be in joules. It's given in kilojoules, has to be in joules because my R is in joules, and my temperature has to be in K to get the units to cancel. And then I just go through and I solve for A. Now what doesn't change is, well, what does change is that we want to calculate a new rate constant then at, not at 298, but at 95 degrees C plus 273, which I think that number is 368 K. That's what changes right there. These other things don't. We've got our A, and we just calculate then a new rate constant. And it comes out to be close to one of the answers. I won't tell you which one, but that's the way you do that problem. And it's fairly lengthy, and I apologize. Some of these calculations require a lot of number punching, but they're really trying to get you to determine whether or not you understand that, for example, in this case, the activation energy is fixed. It's the temperature that changes. Okay, so that's problem 10. And then this is our last chapter 15 question, and it's about a mechanism, and this is what we talked about in class just this morning on Monday. So we have an overall reaction, stoichiometric balanced equation, 2 NO2s plus Cl2 gives us our product. And then a mechanism is proposed that has a slow step and a first step. And then, given the following proposed mechanism, predict the rate law. What would you predict that the rate law, when you go in and do the experiment, turns out to be? And remember, that depends on which step is slow and which step is fast. That bucket analogy I tried to give you. The bucket that's slow, has a small hole in it, fills the second bucket and immediately goes through to fill the product. So our expected rate order, or order for the rate law, is 1 NO2, 1 Cl2, so that would be rate is given by the rate constant times NO2 to the first power, Cl2 to the first power, because that is the slow step, and that is problem 11.